now I think we can start. If you remember on Tuesday, lastly, we were discussing this schematic, and we said that in direct energy deposition systems, obviously we have a laser, and this laser has an focal plane. This is the plane here. Why this was not working? Okay, this is a focal plane, and the energy is actually kind of focused on that specific point, as you see here. And if you are in this range, if your layer is in this range, then that means you can have a kind of an obtain a molten pool and join these powders to the previous layers. But in the above or in the bottom part of this region, we don't have the required energy. EC is actually lower in this, the E is lower in this range. And here we have the energy higher than critical value. But again, in this top region, our current energy is less than the critical energy. So we need to do the manufacturing in this green region. So there's a question. Let me discuss the issue here. So we have a kind of an, not exactly, but we have our molten pool around here. And assume that this is the side view of it. Once you have the actually focal plane around here, then that means you have a liquid material in this region. And once you actually spread your powders or jet your powders into this pool, they will enter it and they will be liquefied and join with the remaining powders. Once your laser actually moves to right or left, once your laser moves away, they will quickly be solidifying. So your aim is actually to jet your powders into these molten pools. If you jet your powders around here, then they will not be melted and solidified with the remaining of your part. You will be actually wasting most of your powders. So the parameters are highly important, as in the case of our additive manufacturing processes. Once you have missed parameters, then you may have thin layers. You may not come up with the proper layer thickness. You will not be able to deposit after some number of layers. Since your focal plane will be, let's say, above, and your material will not be colliding with the previous layer. Let me try to illustrate it. Assume that this is the part you have manufactured a moment ago. Assume we have, let's say, 4 layers manufactured properly, but at some point, your focal plane might be here, and after this part, as you know in the previous slide, we have less critical energy, we have less energy exposed. So once your powder actually spreads around here, they will not be colliding with the previous layers. And since the maximum energy is around here, you can only melt your powder around here. But once you jet the powders into this point, they will not be stationary. Since they have high kinetic energy, they will go away and they will not stay at this point. Since this is a point in air, it's not touching to your previous layers. So if that's the case, you cannot do the manufacturing or deposition. Another important issue while fabricating the first layer, since you start with a substrate, if you remember, I showed you this part, this block is the substrate. You start manufacturing on this part. And in the first layer, assume that this is our substrate. So your focal point should be inside the substrate for the first layer. Otherwise, you cannot have the deposition started. It should be usually around 1 millimeter into this. This part is 1 millimeter. And if you don't bury your focal plane into the part, then you cannot start the deposition. So what happens while we are actually feeding the powders? Since we need to have a kind of a container around the machine. And in this container, first you need to do some fluidizing these powders. Since they are in solid form, by applying some bubbling up some gases, you will fluidize these powders. They are not liquefied. This is important. They are not liquefied, but they are fluidized, which means that they are moving easily. And once you do this fluidization, then by applying some pressure from this container, with the help of the pressure, you can deliver your powders into the nozzle. And they will have, again, high speeds with the help of this pressure drop, and they will be fed through the tubing around your laser heads. Any questions, guys, about these fundamentals? It's quite important. This slide actually discusses the fundamentals of direct energy deposition systems. Okay, so here are the examples. You see two different laser heads. This is our laser, but the whole part is called as the head. Again, we have another head here. They are all laser heads. And the difference of these two examples is that in the first one, we have a coaxial nozzle system. We are feeding the powders around the perimeter of our laser beam. So let me draw a bottom view. If this is your laser beam, then we are actually spreading powders around this kind of a ring. Powders are actually fed through this ring, and this is called as coaxial feeding. But in the single nozzle feeding, obviously we are using a single nozzle, and let me draw again the bottom view. So we'll only have the powders coming from a single point. So this is called as single nozzle feeding. We also have four nozzle feeding. In the four nozzle feeding, we have four nozzles at 90 degrees apart. That is called four nozzle feeding. So they have different advantages. Different companies are, for instance, using coaxial. Some companies are using single nozzle or four nozzle. So that's their differences, variations in terms of other similar technologies. If you look at the coaxial case, we have another difference with respect to the single nozzle example. We have shielding gas. As you see, this is supplied from another, let's say, coaxial region. This gas is supplied from here, and it forms a kind of an shielding atmosphere around your laser and around the powders. You see, the deposition actually is carried out inside this shielding gas atmosphere. So it's actually kind of compressing the powder stream. So your powders will not be actually easily go to the other regions of your table. But in the single powder feeding system, with the help of their kinetic energies, they will be spread around the table. But in this one, it's quite difficult. Again, we will have some amount of material, some amount of powder spread, but not as much as the second case. Any questions, guys, about these feeding systems? Powder feeding technologies. So let's go through their details. In the coaxial feeding, obviously, we have the high capture efficiency of powder. Since we have the shielding gas, we have the coaxial feeding system, so our molten pool will capture most of the powders. And another advantage of using shielding gas, I forgot to tell you in the previous slide, since it's a kind of an inert atmosphere, we don't have any oxidation in the deposition process. But if you don't have kind of shielding gases around, then probably you will have some oxidation inside your deposition process. So what about the single nozzle case? In that, the system is quite simpler. We don't have any, let me go back, we don't have any shielding gas type of feeding system or no special powder feeding system. We only have a kind of an hose and once you apply pressure into your powder chamber, you can spread these powders at a specific point. And this is much simpler. The laser head is much simpler compared to the coaxial nozzle case. And this one actually has better capture efficiency than the 4-nozzle case. As I have drawn the 4-nozzle feeding system, we have 4 different nozzles at different corners, and in that case we have more powder actually spread around. But if you are using a single one, it is less than the 4-nozzle case, so we can say that its capturing efficiency is better than 4-nozzle feeding system. And the advantage of the single nozzle with respect to coaxial and 4-nozzle systems is that you can deposit this material, the powder, into very tight regions, tight locations, or very little holes. If you are doing especially a kind of an repairing task, if you remember a similar drawing I have drawn on Tuesday, this process is quite useful for fixing some cracks, doing some repairing operations. And for that purpose, it's better you use a single nozzle system, since you can easily focus to a specific point and fill these gaps with high pressure of powders. And once you use laser, they will be melted, and you can fix these cracks or kind of openings on your parts. And the only advantage of 4-nozzle system is that you can have more consistency in terms of build height. In the other ones, you may have some inconsistencies. Let me show you an example. I put it somewhere else, but I'm sorry, guys. I'm mistakenly closed the presentation. Let me open it once again. You don't see it right now, so let me share. Any questions, by the way? Yes. Okay, I would like to show you this picture. This is actually the one I have in my hand, and you see that we have height differences. If you look at here, this is the height we have, but here the height is much higher. If you remember on Tuesday, I said that this process is not actually proper for building some single thin edges, thin walls. It's not an appropriate process. With this process, it's better we do some, let's say, repairing task, or we print a solid interior. Otherwise, you will have difficulties. And here at the center, we have the maximum height. Again, on these regions, we have little height. So they were using, in this machine, they were using a coaxial system. They didn't have a 4-nozzle feeding system. If they had, I think we would have more consistency in terms of build heights.
Hocam bir şey sorabilir miyim?
Yes, Bilal.
Şeklin ortalarına yaklaştıkça height'ın yükselmesinin bir sebebi var mı? Hani sizin demin gösterdiğiniz şekilde.
Actually, this one, I just only had maybe few hours to work on this machine. They were trying to make just a demonstration on the machine, and I modified their G code to fabricate such a case. Since they do not actually let me produce such thin walls, they were only producing such kind of coatings or solid products. I modified their G code. Probably I may have made a mistake in the G code, or their capturing efficiency were not good, maybe in some specific parts of the plane. But for instance, at the center, as you see, as you also pointed out, we have a height. Let's say the height is too much, but at the other side, it's not as the center region. I don't have a pure answer for that, but it's probably, I don't know, maybe the machine has some disadvantages at the side of the product, or they had different materials. I don't know, they may be using recycled materials, but there might be many reasons behind this problem. And let's go back to the point we were discussing. Yes, we said that with 4 nozzle, we have more consistency since your friend is asking on the chat, you are actually depositing more powder. Once you deposit more powder, then probably you will be having more powders inside your molten pool, and with that way you can obtain more consistency in the height of the lasers, the height of the layers. But with a single nozzle or coaxial, you are trying to use less amount of powder, and that may result in, as in the example I've shown you, some inconsistency in the build height.
Hocam bir şey sorabilir miyim? Bu four nozzle olduğunda kontrolü falan daha zor oluyor mu single nozzle'a göre?
Can you ask again? I couldn't hear.
Four nozzle olduğunda kontrolü o nozzle'ların parametrelerinin daha zor oluyor değil mi single nozzle'a göre?
The parameters related with the powders are not difficult, but controlling might be difficult, and not much difference with respect to the other ones, I guess. Since again, you need to take care of the build height, you need to take care of the molten pool, and the companies are these days using some cameras. If you remember, they put one on left side, one on the other right-hand side, and try to always capture the molten pool and check whether the build height is consistent, whether the focal plane is at the desired location or not. But I don't think there are much differences in terms of the parameters. So let's briefly discuss the wire feeding case. And we said that this is very similar to fixed filament fabrication. And the thing is that we don't have, obviously, extra material around the table. The volume of the deposit is always equal to the amount of wire actually you are feeding into the nozzle, very similar to the fixed filament fabrication. So the capture efficiency is 100%. We don't have any waste material. And it's especially useful for simple geometries or having some thin walls. This is where we can use wire feeding, or you may have some coating of different surfaces, but obviously not easy. And you may actually produce some lattice structures with the help of it. The resulting product might have some high porosity. So you determine the type of feeding system you are going to use according to the application, according to the part you want to manufacture. So in one case, wire feeding might be much better, but in other cases, powder feeding systems may do better. Let me show you some examples, some example technologies. The first one is called as lens. It was introduced in 1997, and they have a kind of an inert gas chamber, and they process these materials in the inert gas chamber. And with the help of it, they eliminate any oxidation problem. They were using 4 nozzle feeder. And the advantage of the 4 nozzle feeder we didn't mention, but here we can say that since you have 4 different chambers and nozzles, actually feeders, you can have different materials coming out of these nozzles. So you can mix, let's say, copper with steel or other kind of materials together. It's a nice property of 4 nozzle feeding systems. And again, since this process is quite complicated, you need to always monitor the build height. And the thing is that if you have proper algorithms in your controller, you can dynamically change some of the parameters. Once you see that there is a huge difference between the heights, you can feed more material into that region and decrease the focal plane and try to come up with a good print. So in summary, you need to have a closed control system, and your loop, actually your sensor, is the cameras you are using in around your laser heads. That's what, as I discussed, actually the machine after this point stopped, since it realized that there's a huge difference between the size and the center. It didn't continue with the rest of the part. It stopped right at this point, and we couldn't complete this fabrication. This was the lens system, a very old picture, but you can have a look at the newer ones online. And then we have another example, POM, again, it's from USA. The difference is that they have 5-axis. If you remember the company Instack, we discussed on Tuesday. And we also discussed that in direct energy deposition systems, the orientation is not a problem. Since we are feeding the powder at very high speeds, we don't need to have the gravity. Gravity is not a problem for us, so we can even jet powders in a horizontal direction. And again, they were using shielding gas, so most of the companies are using shielding gas around the head, or they are doing this manufacturing process completely in a vacuum or shielding atmosphere. And again, they were using closed control system to control the build height and the molten pool. They were using some CCD cameras, checking the size of the pool. And once they come up with, they realize any problem, they update these parameters like powder flow rate, deposition velocity, and the power of the laser, so that the problem will be solved and they will have a proper print. And they were using carbon dioxide laser, and it's mostly used a good, let's say, type of laser, since the absorptivity is actually quite okay with most of the materials. And once you use carbon dioxide laser, you will have a larger heat effect zone. You should be aware of that, and with this information, you should adjust your speed and powder flow rate accordingly. Here you see the monitoring example. We have 2 feedback sensors. They are camera, actually, vision sensors, one on the left and one on the right. They are checking the molten pool. If they see that there is a difference between the previous layer and the focal plane, then probably they need to do some modifications in terms of the parameters and try to solve this problem. There's a question, but not just lens, but most of the companies are using closed loop control systems to have better products. We have another company. This company is actually focusing on printing larger parts or coating the larger parts with direct energy deposition. Obviously, they need to use high power laser around 18 kilowatts. For instance, they may print some ribs on the available structure. So you have a huge part and you need to have kind of ribs. This is a nice process for the nice machine. With other ones, you cannot do it since they only have very small bed sizes, but this machine, the company Aeromet, actually fulfills this gap by using direct energy deposition system. And since their system is capable of working with large parts, it's quite faster. If you are going to do work on some larger parts, you can decrease the manufacturing time with their system. But the problem is that since they are using huge laser powers and also larger parts, their precision is not that good. And as we discussed with the carbon dioxide lasers, you always have larger heat affected zones. You need to be aware of it and take some actions according to this problem. This is actually the size of the machine. As you see, they have huge columns, and it's probably printing a kind of a shape, not printing, but manufacturing some ribs on this part. It's another example. They start actually with this base. They have a kind of, and this is the base, and on top of this base, they deposit such layers as you see, and they are quite complicated, and you cannot manufacture this part by using any other conventional or any other additive manufacturing process. It's only possible with direct energy deposition systems. There's a question on the chat. Hussein is asking whether the shielding gas can decrease the size of heat affected zone. No, it's not related to the heating zone, as the heat affected zone is just related with the amount of energy you're applying into that region. So it depends on the power of the laser, the type of the laser, and the material itself. The shielding gas is just providing a kind of an atmosphere for not to have any oxidation inside your parts. So let's discuss the parameters, the process parameters in direct energy deposition systems. If you remember our discussions with stereolithography, fused deposition modeling, or fused film fabrication and selective laser sintering systems, they were all solved with some optimized parameters, but it's not the case in direct energy systems. You need to determine the parameters for your specific cases, since depending on the size of your product, you may need to use specific parameters, or depending on the powders you are using, again, you need to adjust some of these parameters. What are they? For instance, the scan spacing, the distance between the path of the, let's say, since again, in this example, in this additive manufacturing process, we need to again fill the interiors completely. So we need to have such scanning patterns, and they need to be close to each other. This gap is quite important. This is a trend, the track scan spacing. And then we have some other parameters. We have powder feed rate, how much powder we are feeding into the molten pool, the speed of our laser, at what speed is moving over the plane, and the power of it. And lastly, we have laser spot size. It depends on the optics. You can try to decrease or increase it. If you increase it, then your accuracy will be getting lower. If you decrease it, then you can decrease the size of the molten pool and have more precise products. So what do you think these three are in blue, but the rest are not? Why these are in the same color? What do you think? If you look at these, powder feed rate, laser speed, and laser power. No idea?
Hocam bunlar kontrol altına alınabiliyor. Öyle bir ortak yönlerimi var.
What about track scan speed, spacing? Can't we control the first and the last one?
Doğru.
Hocam bu üçü birbiriyle bağlantılı mı diyoruz? Yani atıyorum feed rate'i artırırsak transfer speed de artmalı gibi bir yorum yapabilir miyiz?
Somehow what we can say that they are interrelated, which means that you can actually obtain the same result by, for instance, increasing the laser power. I'm sorry. If you increase the laser power, then that means you are actually increasing the size of your molten pool, right? The size of this one will be improved, increased, and you can also obtain this one by decreasing the speed. If you want to have an increase in the size of the molten pool, you can have it by simply changing the laser power or decreasing the laser speed, or what about, but this one is not highly related. I cannot say simply that by modifying it you can increase the size, but these two are somehow related. By adjusting any of these, you can play with the size of the molten pool. So we can say that they are related, but let's have a look at these two. Can anyone tell me how they are related to each other? No idea?
Speed arttırırsak rate'i de arttırmak zorunda mı kalıyoruz acaba?
Yes, if you want to have the same amount of power in your molten pools, once you increase the speed, then that means you should also increase powder feed rate. So let's say what happens if you are increasing the speed but keeping the feed rate as constant. And that means you have less amount of powder actually in the molten pool, which may result in inconsistencies in your build height, and then at some point you need to fix it. So these three are highly related to each other. We say that they're interrelated. That's why I have them in blue. But other ones are not related to the intermediate ones. Any questions, guys, regarding these parameters? Okay, let's discuss some scan parameters. It's again a process parameter in direct energy deposition systems. If you remember one of the early sketches of DED systems, I said that we prefer to have actually different orientations for consecutive layers. For instance, if you start with vertical scanning, then in the next layer it's better you have some horizontal scanning, so that we will be decreasing the residual stress which is building up during this heating and cooling processes. Another thing, once you have such differences in the consecutive layers, you will have a better actually joining between the layers, and your overall strength will also be much better. And this is another issue we discussed actually it in SLA and also in selective laser sintering or melting processes. It's better you have kind of a slight overlap, so that this will increase the strength of your part. And this is another issue we discuss in SLA and SLS systems. The layer thickness should always be less than the size of the depth of your molten pool. Otherwise, you cannot join two layers together. They will be quite brittle. So with the help of the sensors we have, with cameras, with vision sensors we have around the laser head, we can control this deposit thickness, as we have seen the problematic example in my hand. And we need to always take care of these heights and try to adjust the speed and also the powder feed rate, so that we will have a consistency in the build height. There's a question about the jetting speed is related to the powder feed rate. Powder feed rate actually is the speed of the powders. Any questions, guys, up to now? Up to this point, I mean, microstructure cases. Yes, Arda?
Hedge spacing gibi daha anlatabilir misiniz hocam?
Okay. If you remember in SLA systems, assume that this is the contour of our cross section. I'm producing a kind of a square, and we have such scanning patterns, right? And we need to fill the interior of this region completely with powders. But if you have, let's say, huge gap between the consecutive edges, then probably you will not be able to fill the interior completely. You may have some gaps around here. So the hedge spacing is important. But if you have, let's say, your focal point or the size of your molten pool, assume that this is your molten pool. I'm just now giving some numbers. 2 millimeters, okay? The diameter of your molten pool is 2 millimeters. So assume that if this gap is, let's say, 6 millimeters, then we will have 2 millimeters of gap, or I'm sorry, one from here, one from there. So we will have 4 millimeters of gap between the deposited, let's say, material. That will be the thickness of edge, and this is another thickness of the neighbor edge, and we will have a gap of 4 millimeter, right? If the diameter of your molten pool is always 2 millimeters. So, which means that after this layer is over, you will have some regions which are not filled with material. And since in this process we want to have completely filled regions, so you need to set this hatch spacing properly.
Yani hash spacing is set to obtain overlaps dedik ya, hani hakikaten üst üste geleceği kadar bir şey ayarlamamız gerekiyor mu?
Not completely, but let me talk about this example. Again, assume that the diameter of your molten pool is 2 millimeter. Then once you have the distance, let's say you have 2 millimeter of material here, 2 millimeter material here. So you need to have slight overlap, which means that the distance between this consecutive edges should be less than 2 millimeters. If it's less than that, then we will have a slight overlap and you will be actually completely covering the whole slice. And in result, the strength of your part will be much better.
Tamam hocam, teşekkürler.
You're welcome. Other questions, guys?
Hocam ben de şu deposit thickness'ı kaçırdım da tekrar edebilir misiniz?
It's actually we had many discussions about it. Assume that this is an side view. At one region, you may have such a thickness, okay? Deposition thickness, but in other part of the slice, you may have such a thickness. And if you see that with the help of your sensors, vision sensors, if such a difference between these two regions, then you may decrease the speed here. You have, let's say, VA, this is VB. VA should be less than VB in the, let's say, fixing part or in the next layer, so that you'll be depositing more material here in the upcoming layer and try to adjust their height. And in the other layers, you'll have a perfect plane. This is how we do the fixing with the help of the sensors and some other parameters. So now let's discuss a bit different topic. Since in this DED processes, we have many parameters under our control. We can control the amount of powder deposited. We can control the laser power. We can control the focal plane, the height of it. We can control the speeds. So we can control everything related with solidification. You can do the solidification in a shorter time, or you can increase the time you're actually reserving for solidification. So depending on this time, you can obtain various microstructures. We can say that with the help of the parameters, we can adjust the type of microstructures you are going to have in your final product. And in these processes, we can use any type of powders, whether they are metallic or ceramic. The thing is that they should be stable in the molten pool. If you can find any powder, any couple of powders, which are stable always in the molten pool, then that means you can use them in your DED system. Another thing about the powders is that once you have a metal and it has high reflectivity and high thermal conductivity, then that means you cannot easily process it. Why do you think is that? Why such metals having high reflectivities and high thermal conductivities result in problems?
Lazeri yansıttığı için tam bir molten pool oluşturamıyoruz sanırım.
Yes, since if it has high reflectivity, then some of the laser power will be reflected away and the thermal energy will not be actually distributed in that molten pool. In that case, your energy level will be less than critical energy level. What about thermal conductivity? Again, we have a similar issue. If the metal has high thermal conductivity, then that means the dissipated energy actually will be transferred to the neighboring zones, neighboring regions. And again, once it's done, actually, your energy level for the specific molten pool will be decreased, and you will not be able to melt the new powders inside this pool. So that's why we don't prefer to have metals or metal powders having high reflectivities and high thermal conductivities. And in summary, actually, we can say that any material which can be weldable is also easier to process on DED systems. And the ceramics are quite difficult. That's why we prefer to use them in kind of a matrix. We have metal matrix and put some ceramic powders inside it so that they will be easier to process. And another advantage of this DED systems, we can have some gradient combinations, gradient material combinations. I think we have an example here. You see a test part, and on this left-hand side, we have titanium 6-4, but on the right-hand side, we have titanium 2030. You can see this smooth transition from one type of alloy to the second type of alloy. And it's possible with adjusting the powders inside your nozzles, and it's a nice property of direct energy deposition system. But these are still research. We don't have commercial machines actually fully producing such gradient structures. So what happens if you have high solidification cooling rates, which means that your laser is moving in a faster way and your molten pool will quickly be solidified, and with the help of it, we'll have many advantages. We will be suppressing the solid state transformation. We will have some supersaturated solutions. These are some metallurgical properties. In summary, we can say that we'll have fine microstructures, very little fine microstructures, which results in high strength. So it's actually we want to have in our processes all the time. If you have them, then your mechanical properties will be much better. And another issue about microstructure thing is that by adjusting again these parameters, the solidification settings, you can have different microstructures in one region and other type of microstructure in the second part of your, let's say, same part, which is a nice property again. And this is not possible with any other additive manufacturing or conventional manufacturing operation or casting operations. You can always have various microstructures in your part. Here you see an example, for instance. This left part is our substrate. Kind of, maybe I can say that this part is substrate. And then we have the heat affected zone. And this is the newly deposited powders. You see we have, after the solidification, we have larger grains, but during the deposition, we have some longer grains formed. And these are all possible by adjusting the parameters. Probably after solidification, they will be shortened, but again, it will be a bit different than the previous layer. So we will have, obviously, during the solidification, some residue stresses actually develop. And once you have them, and that means you may have cracks on your part during the fabrication or just after the fabrication. And this might be a bit quite problematic. So you should be adjusting the parameters properly and not have any cracks during the fabrication or after your part is taken out of the machine. And this happens usually once you are dealing with dissimilar materials. So you need to have some experience with in terms of material and try not to have such cracking problems. And if you are using these materials, dissimilar materials, then you may have some thin interlayers, which are compatible with the previous and the upcoming layer. With the help of it, you can try to eliminate the problem between dissimilar materials. And once you have such interlayers, that means you are increasing the bonding between the layers, and with the help of it, your yield and tensile strength will be improved. But the ductility, obviously, since you have tighter, let's say, microstructures, layers, you have worse ductility. And you can see some crack examples. This titanium carbide, and we can easily see that these parts are cracked. We have another one here, and some micro cracks inside. So these are all due to the residual stresses developed during the solidification stages in our DD system.
Hocam,
So what are the relationships? Yes, question?
bir şey sorabilir miyim? Hocam bu solidification'da fine microstructure oluşuyoruz dedik high solidification'da, ama daha sonra solidification crack oluşumuna neden oluyor dedik. Yani tam ikisi nasıl aynı anda olabiliyor, onu tam anlayamadım.
These cracks actually happen not with high solidification things. This is due to probably dissimilar materials, some other missed parameters, let's say. But if you set all the parameters properly and have high solidification rates, then probably you're not going to have any microstructure. And this microstructure may happen due to, let's say, some gases inside. If your shielding gas, shielding atmosphere is not proper, you may have these cracks also. But it's not highly related with the solidification rates. So let's have a look at some relationship between microstructures and other parameters. Once we have high solidification rates, we can have casted kind of microstructures, very similar to the casted products. And these microstructures will obviously depend on the local parameters, the local solidification conditions, not just the whole parameters, but at a specific point, you may have some heat develop, some thermal stresses develop, and they may result in, again, as we discussed, some specific cracks. These are all due to some misparameters in that specific region. So you need to be careful all the time. Try to monitor your molten pool, the height of your layer, and try not to have these problems. So if you actually have some experience, you may do some calculations in advance and try to obtain proper parameters for your desired microstructure type. But this obviously needs high experience, high, let's say, computational resources. It's not easy to obtain the appropriate values of these parameters. So what are the advantages and disadvantages of these processes, direct energy deposition processes? First of all, since we are applying these powders at very high pressures, we can obtain high density products. And another advantage, their microstructures are all controllable. You can have finer or coarser grains depending on your parameters. Another advantage, by using different types of powders and having different settings at specific locations, you may obtain functionally graded components. Another thing about as an advantage, you can do some repairing, fill the cracks with material, or if some part of the some region of your part is broken, then on top of it you may construct these actually broken parts. Or you can do some refurbishing, which means that you can make it as new and try to use in different applications. And this mostly utilized for turbine blades, since they are difficult to manufacture parts, they are expensive. So that's why people try to use DED to repair such products. Another thing we can do with DED is to apply some coating on surfaces. If you remember from the Instack video, they were coating a semi-spheric hemisphere and try to increase the surface roughness of the part. Or you may have some very resistant products as the coating, and this will increase some of the properties of your parts.